So welcome back and thank you for the session that we had yesterday. I had a great time. I hope that you had a great time as well. So in front of us today, we have the most practical session so far, where I'm actually going to do some programming. And I know that a couple of you have programming experience. You might even have Python experience. Some of you might have only tried programming once or twice before, and a couple of you might never have seen programming or never done that. I think it's important to go through an example like this at least one time. So when you hear terms like artificial intelligence, machine learning, deep learning, neural networks, etc., you know how it's being done in practice, so that it's not only words to you. So that's going to be the first part. I think that's going to last for 90 minutes or so. So the first break might be a little bit early. And then we will be back for the final session where I'm going to cover blockchain, cryptocurrencies, decentralized finance, non-fungible tokens, Bitcoin, Ethereum, all of that kind of stuff. Does it sound good? I can see a lot of nodding. Thank you. So let's jump into it. The first thing that I want to say is that I have updated the URL. There was a little bit of a misspelling yesterday. Sorry for that. That was my keyboard. I'm blaming that one. But you can now go to bit.ly/Oxbridge-masterclass. And if you go to the website, it's showing this one. Does it work for you? No? Can someone give me a thumbs up if that works for you or not? Yes, I have one thumbs up. It's only logged into my Bitly account where I created the link. But so if you go to the course website, then you will see that I've updated the links to the lecture slides. So you can actually follow along now. I have all of the materials. If you have your laptop in front of you, if you actually want to do some coding, I call that a code along or something like that. There are sing along sessions that you can have. But if you're comfortable with these tools, you can go to the course website, you can scroll down, and the notebook that I'm going to present is called Titanic here. So you can actually press that one. What will happen then is that you will open up what is called a notebook. So this notebook is hosted on Google Colab. Google Colab allows you to run Python code in your browser. You don't need to install anything. You don't need to do anything complicated. You can even have a GPU, which is special hardware to do calculations and train these models very quickly. So if you want to try that out, I've set that up for you. And all of the slides that I'm going to present, even on the blockchain topic, are live on the website. So agenda here now is that I'm going to cover the tools that you use in order to build real-world AI and data systems. And we're going to do that by looking at this Titanic survival analysis challenge. And again, if you want a short link to the notebook to run it in your browser, you can go to bit.ly/Predli-Titanic. And that should work. But so I'm going to switch gears a little bit now. Let me know if my screen sharing works now also, because I'm going to keep on changing windows. So can anyone tell me what they're seeing here? And what's a terminal? Yes, so this is a way of interacting with your operating system. So many times when you build like AI projects, when you want to use Python, etc., you interact with those tools through your terminal on the computer. If you've never seen a terminal, that's fine. But I just wanted to show you how I actually launch a notebook on my computer and not in the browser. So either you can press the link that I showed you, or you do it like this. So first of all, I would have to tell my computer that I'm going to use Python and a couple of packages in order to train artificial intelligence and machine learning models. So here I have what is called a virtual environment that I'm activating, that is called DataX. And that has all of the tools that I need in order to train these models. Then I'm going to find the folder that we're going to work in, and I actually have that open here. So if we go ahead and open that up, you will see the files that I'm going to use, and I need to zoom in now. This will be a little bit small for you in the back, but basically here I have a couple of notebooks. Their ending or their file extension is IPyNB, that stands for notebook. And I also have a folder that is called data. So I covered that yesterday, that in order to train machine learning models, what you did was that you let the computer learn from patterns in data in order to come up with their rules on how to make predictions or decisions. And what we're going to solve today is a prediction problem. Before we jump in to the actual code and notebook, I want to show you the data that we're going to work with. And it's this train.csv file. So the data we're going to use in order to train our machine learning models. I hope that all of you have seen Excel before. It can actually be quite a valuable tool, believe it or not. I still use it at times. Are you able to see this now, you in the back? Yeah. Wonderful. So what we have here, the data we're going to work with are passengers who were on board of the Titanic. This is not simulated data, but these are actual people who were on board of the ship 100 years ago, approximately, when it sank. As you can see here, the data is structured as rows and columns. So this is what is called a tabular data set. Basically, every time you have a spreadsheet, that's a tabular data set. Every row is a passenger, and every column in machine learning lingo or in AI terminology, every column is a feature or a characteristic of that person. So if we take the first person here, we have a passenger ID. That doesn't seem to carry a lot of information. You can see that that is an integer or a number that keeps on increasing by 1. So that's just a way for us to like order them and be able to identify them. Then we have maybe the most important column of all of them, because the machine learning classifier and model that we're going to train is going to be a predictive model that can predict if a person survived or died when they were on board of the Titanic. So we're actually going to be able to solve this now, and all of you will be able to understand it, even though you've never programmed before. Trust me, it will be a little bit of a journey. But so the survived column, you can see that that is populated by zeros or ones. So the 0 is a really bad number, because that means that you didn't make it. And the 1 is a happy story, then the person actually survived. So that's the first column that carries information. Second feature is called P class. That stands for passenger class. Now that is a socioeconomic proxy. So it basically means it can take on 3 values here. It can either be a 1, a 2, or a 3. So it indicates if you're from the working class, then you will have a 3 in that column. If you're from the middle class, it will be a 2. And if you're from the upper class, that will be a 1. So it basically means how wealthy you were, etc. Then we have one column that is called name. So we have the last name, we have a title, and then we have the first names. We have one column that is called sex, and that is the gender of the person, male or female. One column, age, that is how old the person was at the time. You can also see that for some of these columns, we have missing values. I'm going to address that later, but it's important for you to see, like even in Excel, we can identify them. Next column is called SIB-SP. That stands for siblings and spouses. So if you had any sibling or any spouse with you on board, this number would increase. So here you can see a person that has maybe 2 siblings and a spouse with them. Next column, PARCH, is parents and children. So if you had your parents with you, or if you had a child of your own, that would increase in numbers. We have the ticket number that the person was assigned. We also have the fare. So how much did the person actually pay to be on board of the Titanic? What was the cost of the ticket? Then we have the cabin. So where were they staying on board of the ship? However, here you can see that we actually have a lot of missing values. So we don't have that data on many individuals. Last but not least, we also have a column that is called embarked. So that indicates where you boarded the Titanic. It can either be S, that stands for Southampton. It can be C, and now you will have to correct my French, but that stands for Cherwell, something like that. And then we have Q, and that's for Queenstown. So 2 places in the UK and 1 place in France. That's where they docked. People boarded the ship, and then it went to go to New York. And after a couple of days, it unfortunately sank, even though it was supposed to be an unsinkable ship. Everyone has seen the movie, right? Do you still do that in your generation? I saw some people over here saying no. But yeah, very famous movie, kind of good, kind of sad towards the end. I would recommend it. And it also tells the story of what happened on this very infamous ship wreck. Now, I'm going to open up the notebook that you saw. And I have that here that I can show you in a better way. So this is the same example, like the one that I linked to, that you could open up in a browser tab. Now, before we jump into the actual code, I want to talk a little bit about this notebook. Because the tool and how we're going to leverage Python and the libraries to train machine learning models is a Jupyter notebook. This is really good in order to communicate scientific research, if you're doing data analysis, and if you're doing anything in AI. Because what you can do is both to have these markdown cells, so you can actually write information and guide readers of your work to what is happening when you're doing your analysis. So if you double click on any of the text, you can actually go in and change it. And I'm the author of this notebook that you see here. So these are only normal text cells. And what I want to mention here quickly is that whatever machine learning or AI use case you can think of, so if you have an idea for a smart model, for some type of use case or implementation that you want to do, you can actually make that come alive with the tools that I'm using here now. And they are very, very accessible. They're also free to use. So no matter if you want to build a recommendation system like we talked about yesterday for product recommendations on a website, you can do that in these tools. If you want to do fraud detection for a bank, I worked a little bit with HMRC here in the UK and looked at their tax fraud system. You can do that with this. If you want to predict optimal prices for certain products, etc., all of that can be done with the tools that I'm covering. We also saw a version of this graph here yesterday. I said that we had a cutoff then at 2018. This is how you can see how Python has progressed over time. So every developer is basically converging to using Python and the tools that I'm showing you here. And that also means that it's a great developer ecosystem. And as I said, this is open source. You don't pay any license fees, etc. So some of the tools that you can use in order to set this up on your own computer, and also the libraries that I read in now when I activated the DataX environment in my terminal earlier, are TensorFlow, scikit-learn, Pandas, Keras, Matplotlib. Those are a lot of words. I'm going to show you what they actually mean in a little bit. And every time a new algorithm, a new approach, a new methodology gets released in a research paper, the community around Python is very quick with actually implementing it into a library so that you can use it. Usually it only takes a couple of hours or a couple of days, or the researchers that has the new approach, they will already have implemented it so that you can use it. And this also works with big data. So if you have terabytes of data, then no matter how big the data size is, you can work with these tools that I'm presenting also. But so now we're going to start to look at this actual like Titanic problem. And you might wonder where I've gotten this example from. So there is a very famous machine learning competition website online, and it's called Kaggle.com. So Google bought this company 2 years back because they saw the tremendous value that it provided when it came to actually experimenting with artificial intelligence and machine learning. So Kaggle is a website where research groups and companies, they can post challenges. One example of a grand challenge that was posted on Kaggle 2 years back was research groups that had X-rays of lungs. They wanted to have better tools to detect tumors in those lungs. So then they posted a challenge here on the website, and they said the team that can create the model that has the best accuracy will win $1 million. That's a lot of money. So the best computer vision researchers in the world that could analyze these X-ray scans, they worked on this task for half a year. So what you get that then is a subset of the data will be posted. So you will get some data. And if you remember from yesterday, it's supervised machine learning. You will get X-rays that either say this doesn't contain a tumor, or you will get X-rays that says this has a tumor and here's the place for it. Then you train an algorithm and you upload it to Kaggle. Then they will take some data that you haven't seen, that they keep to themselves. And they will see what accuracy you have on that data you haven't trained on. So the one who won the competition got the $1 million. And they do this for companies also, banks, many times. They are posting data on their customers that is anonymized. And then they might want to improve their credit models. So then you can win a couple of $100,000 if you're really good at that. We have insurance companies, et cetera, et cetera. But one of the most fun data sets, according to me at least, is the one that we took a look at in Excel. So that's the Titanic data set. And that has been curated by the Kaggle team because they want people to experiment with that data set so that they can see new approaches for developing machine learning approaches and prediction models. So the competition here is to create the best prediction model that can predict if a person survived or died. That is called a binary classification problem because we only have two outputs. It's either died or survived. So then we can go back to the notebook. And here you have the front page of the New York Times when the Titanic sank. They didn't even have the count for how many people had perished and how many people had survived. So just as a precursor here now, the Titanic sank on April 15, 1912. And when it collided with the iceberg, then 1,502 people out of the 2,224 passengers actually died. So more than half of the people who were on board of the ship didn't make it. That's important for us to know. One of the main reasons why so many people died was because they were overconfident in the ship's capabilities. They didn't have that many lifeboats that they actually needed in order to save more people. So after that, a lot of safety around ships and cruises increased significantly when the Titanic had sunk because it was such a huge tragedy. So now from Kaggle, we have received a data set with 891 samples. So that's the number of passengers that we have data for if they survived or if they died. And our goal now is to train the best AI model to be able to predict if a person did make it or not by only looking at the columns that I showed you. We don't have anything else. So we know the name, we know the age, siblings and spouses, parents and children, etc. So in order to do that, and this is, let me actually restart here because I see that it has been run one time. So that I'm not cheating. I'm actually going to do this in real time now. Hopefully there won't be any hiccups. It's always a little bit exciting when you do a live demonstration with code. But so now we don't have a text block here anymore. You can see that there is a lot of Python code. It basically says import on many lines here. What I'm importing into Python when I run this code block are the libraries and tools that I'm going to use in order to solve this. I only make the import once, because then I have the capabilities that these tools provide. The package and the library I'm going to use the most is called pandas. That can handle spreadsheet data, so data that are in columns and in rows. We also have a package called NumPy that stands for numerical Python. With that, we can do multiplication, matrix multiplication, vector addition, etc. We have some tools for producing plots. If you want to visualize the data, you can use matplotlib and Seaborn. And then we have this big block down here where I'm importing machine learning algorithms. And I'm going to use many of them. So we're not only going to train one AI model, we're actually going to train 7. And towards the end, we will even train a neural network. And I'm going to show you how that works. So now, in order to run this, you can either have, I think, if I bring up the toolbar, you can either be in this code cell here, and you can press the run button up here. Then if we go back up, you can see that within the square brackets here, we have a 1. If I run that a second time, we will run it again. So the way that a notebook works is that we have a so-called Python kernel in the backend. So we basically have a Python engine that is waiting for commands to be sent to it. And then when we send these commands to the engine, they will evaluate them, read in the packages, and then it will update the number within the square brackets there. How many times we have run different code cells in this notebook. Now, it's a little bit cumbersome to control this with the mouse, I think, to always go up to the run button up there. So of course, there are keyboard shortcuts. The way that I'm going to run these code cells is that I'm using shift and then return, and I can do that instead. So if I want to run this now, what it says here is that I'm using the package pandas. If you remember that, I said import pandas as PD. Then I can use the capabilities of pandas. So pandas works on spreadsheet data. And what I need to do first is to actually read in the data to my analysis here. It doesn't know what data I'm going to work on. So I'm using pandas with PD. And then I have a period. And then I said read underscore CSV. That stands for read the comma separated value data file, if you want to know the details around it. I'm storing the results in a variable called df. So that's an abbreviation for data frame. So I used shift return now. You can see within the square brackets, we have a 3. That means that I've evaluated it. Now I'm going to remove these like toolbars and headers so that we have some more space. So now I have a variable with all of the data. You remember what I showed you in Excel, right? If I run only df here now, then what happens is that it will evaluate the command. And as the output, it will show me the data frame or the spreadsheet that I'm working with. So this is the exact same thing that we saw in Excel. And we have 891 rows. That's also what I told you. I wasn't lying. That's how many people we're going to look at. And we have 12 columns in total. If you don't want to print out everything, there are many commands that you can do on top of these variables. So if I run .head as a command, it will only show me the first 5 entries. And bear in mind, row number 1 is called 0. So that's why we have 5 here in total when we enter row 4. So now we're going to explore this data first. And I want us to make a couple of hypotheses together. In the notebook, I've included a picture that describes the data, but I already did that for you in Excel. So the data we have on Titanic passengers, we know if they survived or died. That was encoded as 0 or 1. We know the passenger class, first class, second class, third class. We know the name, we know the gender, age, sibling spouses, parents, children, ticket number, passenger fare, cabin, and port of embarkation. So where they went from. That's all the data we have to work with. We can also run other commands. So to preview the data from the bottom rows, instead of using head on our data frame, we can use tail. and that will show us the bottom rows. And this tool here, Pandas, that I've imported, it is so powerful. I use that all the time when I do data analysis. I don't open up Excel anymore, even though I said it's still a powerful tool, because this enables you to do so many things. And also when I've been working with tech companies in the Silicon Valley region, all of them use this tool that we're now exploring what it can do. Another method that we can run on our data frame, if it's a Pandas object, is describe here. And that will give us a lot of insights into the data right away. So for all of the numerical columns, the columns where we had numbers, we can right away, by running the describe method, it says, okay, what is the average survival rate for the passengers that we have data on? And as you can see, that is 0.383838. That means that only 38% approximately of the passengers that we are going to analyze, they survived. That seems to be in line also with what we saw with the full passenger set. Now we're looking at a subset of 891. The mean passenger class is 2.3. That means that most people were actually from the working class or the third class. The average age, 30 years old for the passengers. Also important to know, now we have what is in between there. Siblings and spouses, people on average had 0.5 with them. Parents and children, 0.4. And the average ticket fare was $32. That sounds kind of high to be in 1912 dollars. But we can also see why, because what you want to do when you have a data set like this is that you want to analyze and see that there are no outlier values or any unreasonable values. And with this describe method, then we can analyze right away that, okay, for the age column, for example, the person with the lowest age is 0.4 years old. So that's a baby of some sort. And the oldest person is 80. We can see the minimum value and the maximum value. And then what is called the 25th percentile, 50th percentile, 75th. But it's important here because we don't have any people who have a negative value of age. That's not the minimum. And we don't have someone who is 250 years old. So that's a good sanity check that all of the data is actually consistent. We can also see that most people actually paid around $14 if we look at the median. So that's the 50th percentile. And then we have a huge gap from the median up to the maximum value. So the person who paid the most for their ticket was $512. So only with that command, we're doing a lot of data analysis. We're getting to know the data sets. And in some sense, we're also getting to know the passengers on board of the Titanic. We know that they were around 30 years old. We know the survival rate and how big of a family size they had. We can also visualize the data if you want to get to know it even better. So if you run the method or the function .hist, then we will produce so-called histograms. They will show you the distributions for every feature, every column. Now for passenger ID, I said that doesn't give us any information. You can see we have one for every number. But for survived, we can see the actual numbers. We have around 550 that died, and maybe 320 or 30 that survived. For passenger class, this is interesting. We said that most people were in the working class or third class, but we can actually see there were more people from the upper class than the middle class, and then a lot of people from the working class. When it comes to age, we didn't have that many children on board. So you can see 0 to 10 and 10 to 20 are kind of low. And then it shoots up with people who are 20 to 30. That's the majority category. And then it goes down. And here we have the oldest people who were on board, like 70 all the way up to 80. Siblings and spouses as well. So the most common thing is to not have any siblings and spouse. And then we have some people who have 1, and then a couple even had 8. So that is called like an outlier, where we have some values that are very big. It's a long-tailed distribution, if you want to speak AI lingo or language. Parents and children, also long-tailed. And the fair is very long-tailed. And what I mean by that is that we have many, many samples who paid between, I think it's 0 to 50 in this graph. And then just like one sample that paid more than 500. All of this analysis is important to do to get to know the data set. If you don't know what you're working with, and if you cannot understand the problem you're exploring, then you're going to be fumbling in the dark and you're going to make mistakes. So we want to build up knowledge. Now, the very last thing that I want to do is to look at the balance between people who survived and died. And this is because we're going to design predictive models. And when you're creating a prediction model, you want to evaluate its accuracy. No worries. So you want to evaluate the accuracy of the model. And as we all know now, the people who died, that was 549. That's what we have in the data set. And the people who survived, 342. If we take the majority category, and that is the number of people that died, and divide that by the total number of passengers, what we will get then is the so-called baseline. So first of all, would anyone here say that we have a balanced data set? And can someone guess what even a balanced data set is? What would be a perfectly balanced data set? Yes. I like all of the answers, and you're very close to what I'm looking for. Most values are the same, I heard.
Half of the values, for example, in this case, half the people would have died and half the people would survive.
Bingo. Perfect, Harry. So a balanced data set would be if we had 500 people that survived and 500 people that died. That's a perfectly balanced data set. Now, if we then took any person at random and we predicted if they were gonna survive or die, we could do that with a coin toss, right? And 50% of the time we will get the right answer. That is not the case right now because we're working with an unbalanced data set. So we have one category out of our two that has more values than the other one. So if we're creating a model in order to do predictions, we need to beat what is called a baseline. And the baseline in this case is not 50%, but it's actually 61.6%. And if we don't create a machine learning model that is better at predicting the outcome here than 61.6%, then we could take the model that only guessed died all the time, and that would perform better. So if we had a model that only said die, die, died, it would on average get 61.6%. And if our models then get 55%, then it's really, really crappy. So we need to be above 61.6. Everyone is following so far. Excellent. So this is what the data looks like, again, just to remind us. And we can start to get some insight from this already. So in order for our machine learning models to be able to predict if a person has died or survived, there will need to be information in all of these columns that can tell us something if they are likely to survive or die. We are only as smart as the information we're given as the data that we have. So I might have one hypothesis, and I might say, okay, the passenger class, if you're from the upper class, middle class, or lower class, or working class, that might actually be telling if you're going to survive or die. Do you agree with me? Would that be the case?
Yeah, mostly that gender, females and children would probably.
That's another hypothesis. But so if we think about the passenger class, let's pause on that column and that feature just for a minute.
Because they're likely to be at the bottom, yeah, the third class, at the lower end.
So the working class might have cabins that are far under deck,
Yeah,
right?
so likely to go down first. But I
Yes.
think on our graphs we saw that most of them survived second class. No?
No, we only saw the
Sorry.
columns one by one, so we
It was
didn't
just
see any.
a sample.
Yes.
Okay. We have more people from the sample.
But who do you think are most likely to survive? People from the upper class, middle class, or working class? Yes, and Katja had a good theory behind it, right? That people from the working class, they might have cabins that are far under deck. It's harder to get one of the lifeboats. They had too few, so they might already be full when you have climbed the stairs and gotten up to the deck. We can actually check this with Python. So when we have that hypothesis, what we can do is that we can run the command here. So I'm only quickly going to explain what happens. It might look complicated, but it's actually easy. Here we're taking out the columns, passenger class and survived. Those are the two that we want to look at. Then I say I want to group by passenger class. So I want to create 3 groups. And then I want to calculate the average value for survival for those 3 groups. So I'm taking passenger class, I'm looking at the average survival rate, and this is what it looks like. So if you were from the upper class, you actually had a 63% chance of surviving. That's a lot higher than the average and the mean. If you're from the middle class, it was 47%. And if you're from the working class, it was actually kind of disastrous. It was only 24%. So already from this, we can start to see some correlation. We can see that the data is telling us something that might be valuable for our prediction models. Now, another thing that I want to show you is that I said that we had some missing values. So we can run one command that is .info on our data frame. That will show us what type of data we have. If it says int64, then it's a number. If it says float64, it's a number. If it says object, that means that it's a string and that is text information. So if you remember from sex or gender, then it said male or female. It wasn't 0 or 1. Also embarked, that was like S, Q, or C. All of them are objects. We can also see if we have any missing values here. So if you remember, we had 891 samples in total. This command will tell us how many entries we have in every column. For the age column, we only have 714 entries. That means that we're missing almost 200, right? For the cabin, we only have 204 entries. Then we're actually missing a majority of the information. We need to do something about that because machine learning algorithms cannot work on rows where we don't have a value. So for the sake of this demonstration and the analysis that I'm going to go through now, I'm actually going to drop a couple of columns to make it easier and also to showcase a hypothesis that I have. So when you're a machine learning practitioner, when you're working on a real world data set like we're doing now, there is not one answer. No one has the correct answer to this, but you build your own hypothesis, you experiment, and you try to be better than everyone else who is competing at Kaggle. But there is not one correct solution to this. There are thousands of different ones, and they have strengths and weaknesses. So what I'm going to do now is that I'm going to drop the fare column, what the people paid for their ticket. That is actually kind of a useful feature, but that's for the sake of time. I'm not going to handle that. We're going to drop cabin because there were way too many missing values for that one. We only had 200 populated values. I'm going to drop the ticket number because that is only noise information, and passenger ID because that was only a number that incremented by 1 or increased by 1. So I'm removing them. And the data I end up with is the data that you can see here now. So this is what we're going to use in order to train our AI models. Now, what would you say is valuable information here in order to be able to predict if a person survived or died? Passenger class, we saw that earlier, that had some differences in survival rates for the different categories.
And the survived.
So the survived column is the so-called target column. That's what we're trying to predict. That's the most useful one. Age. And why would age be important? Mhm. Exactly. Sorry, again, saying.
And the movie, they had a way for rescue to come, and it was very cool. So
Yeah.
all the people not dying.
Yeah, but that feels possible.
What if somebody was worried about themselves?
The work they want.
I love that we have some debate here now, if age is valuable or not, or if old people or very young people tended to make it or not.
But I think sex as well. Yeah.
Yes, so we have age, gender, passenger class. Those are the three that I've heard might be important. Anyone else think that something else is important? we can rebrand it as gender.
Parents and children.
And why would that be important?
If you have a child, you dictate out, and if you have a kid, it might break you down.
Yes.
Are you gonna drop the name from like maybe just like the one person who was like really important, like you're up to five, but probably not.
Is every person has a unique name, right?
Yeah.
Is that data that we can generalize then?
No.
No.
Well, maybe there's two Thomases, and it might, and both those Thomases survive, meaning that Ian suddenly favor Thomas with 100% chance of surviving. So.
And that would be called noise.
Yeah. So you probably want to drop the name.
Okay, drop the names. Anything else that we should drop?
Where they embarked from?
Spouses and siblings.
Where they embarked from, spouses and siblings. Should we keep everything else? So we keep parents and children, but we don't keep siblings and spouses.
No, we keep.
But we drop where they embarked from.
Well, siblings and spouses are much more
Yes. And it might also motivate you quite a lot to like save your child or, I don't know, your spouse or not. We will see. We're actually going to use all of these columns. There is a reason why I dropped fair and the other ones in the beginning and then showed you this. So we need to build up hypotheses why these are important. And I love the discussions that I heard here now when we talked about the age column, when we talked about gender, when we went into maybe the embarked and the name column. So if we only address the name column first, at least I have the hypothesis that your title can have a lot of information. So whether you're a Mr., if you're a Mrs., if you're a Miss, or all the other titles that are in this data. That is actually something that can generalize. We're not going to use Thomas or any type of last name and try to map that to royalty or whatever it can be. Yes. And that would be overfitting to the data set like we discussed yesterday. And then when it comes to the embarked column. So we know that the Titanic docked in Southampton and Queenstown here in the UK, and also in France, in Cherwell or something like that. There might actually be different cultures on how you handle a situation like that. And that's why I want to keep the port of embarkation to see if we can see any cultural differences. Yes, that's also a good hypothesis. And this is exactly what you should do in the beginning before even started working on the data. You should try to figure out what is valuable in order to solve the task and the problem that I have at hand. And now we have discussed this extensively. Are you ready to solve this problem now? Yay. I definitely am. So what we're going to do first is to look at the name column. Then we have the patterns for the name. They look like this. We have a last name. So that's Brown for the first person. Then we have a comma. It's a white space. Then we have the title and it ends with a period. And then we have the first names. So what I want to do now in this pattern, it repeats itself for every name. I'm going to use Python to only extract the title. In order to do so, I need to be good with my programming. So you can see the line where I'm doing that here. I'm looking at the name column of my DF object, my data frame. I'm using string, that's a text command. I'm extracting the pattern that is a white space, any character that is uppercase or lowercase that ends with a period. So that's the pattern I'm looking for. And I'm doing that for all the names. Then I'm storing that in a new column called title. So if we do that and I run df.head, you can see that I have title here to the right. Kind of beautiful. A lot quicker than Excel, at least for me. Now, we want to make sure, so I don't want to go through the 891 passengers and see that we actually have extracted the right title. Instead, we can do a sanity check. So what we can do is that we can cross-tabulate this with the gender of the person, only to make sure that the title we have extracted makes sense. So if we do that, we end up with a new data frame that looks like this. Left column, female, right column, male. And we can see that we had one person on board with the title captain, and that was a male. That makes sense. We had two colonels, both male, one countess, that was a female, one Dawn, that was a male, 7 doctors, 1 female, 6 male, 1 John Keir, I don't even, we had 1 lady, 2 majors, 40 masters. Can anyone tell me what the title master indicates? I know that it's a title here in the UK, and that it has been fairly common. So we have a master in the room, at least one. But yeah, I think it's around 15 or something like that. Maybe it's under 18, and you're correct. But all of them are male. So that's very important. The extraction and the parsing of the data that we did seems to be correct. We had 182 miss. Then we had mademoiselle and madame, 517 misters, 125 misses, and then some more titles. As you can see, many of these titles, we only have one sample or one data point from. That is never going to give us any information when we're trying to predict if a person survived or died, if we only have one instance. That's just what we discussed around the Thomas person. If we only have one Thomas, that person survived, and we're going to say every other Thomas will actually survive. So what I'm going to do now is that I will group all of the rare titles into one category, and I'm going to call that rare. So we're not going to take away any information that we have, because all of them are on different ages, passenger class, etc. That might be valuable for us to know. But we're not going to look at the title for the people that we have just a few samples from. And that's what I'm doing here. Don't be afraid by the code block. It might look intimidating, but it's very simple. So for the title column, I'm going to replace the titles that are lady, countess, captain, colonel, dawn, doctor, major, etc. with rare. All of them are going to be called rare. Then for the title mademoiselle, that's French for miss. MS, that's also miss. And then madame is Mrs. So that's I'm cleaning up the data in this step. Now we can do the same analysis like what we did for passenger class. So we can actually see how likely were you to survive if you had a specific title. Do you think there's going to be a discrepancy here? I heard, Ladies with children.
Likely to be given a lifeboat.
So then that would probably be the misses, right? Because they will be married, they probably have kids, and the miss won't be married. Maybe they don't have children. That wasn't common back then. That's one hypothesis. Anyone else? What title do you think is most likely to not make it? Yeah, but that's in the rare category now, so we cannot single out the captain anymore.
It's just Mr., Mrs., and Miss, these 3 categories we have.
And rare and master.
Oh,
So we kept master also. let's take a look at it. So if you were a master, congratulations, Harry. 57.5%, a lot better than the baseline. If you were a miss, it was 70%. That's a lot higher than the average. If you were a missus, so that was a really good hypothesis, it was actually 80% chance almost of surviving. The rare column, and this is also what we want to see, that's very close to the average or the mean survival rate, 35%-ish. And then we have the misters, catastrophic. You only had a 15.6% chance of making it during the Titanic accident if you were a mister. So back then, people were gentlemen, ladies and children first. A lot of men actually didn't make it. And we can see that by only inspecting the data and doing this brief analysis that we have done now. So only extracting the column, very important, because we can separate out masters from misters. That gives us some information. And also this discrepancy between miss and misses. And not only gender, that will give us a much more crude estimate. It's also very easy to use the plotting tools or visualization tools that I imported in order to look at the absolute numbers. So here it's only like 2 lines of code. We look at survived and title. And then I want to change the axis here. But you can see how many misters actually died against survived. And then you can see that it's much more likely to survive if you're a missus or a miss. And then master, and then we have the rare category. So this is not in percentages, but in absolute numbers. So the data that we have right now looks like this. One thing that I haven't said so far is that in every column where we have text, our machine learning algorithms, they cannot handle text. They can only handle numbers. This is mathematics. So if you're going to try to multiply something, you cannot multiply 4 with male. That doesn't say us anything in mathematics. So we will need to convert all of the text columns into a numeric representation, and that basically means a number. And we're going to do that with the title column now first. So here we had 5 categories, and I can use pandas to do this again. So I want to get some so-called dummy variables. I'm running pd.getDummies on my title column. Then I'm storing that in my data frame like this. And when I'm done with that, I'm actually going to drop the title column and the name column. And instead, it looks like this. So I've converted all of the titles to one unique column. And as you can see here, I've used so-called one hot encoding. What that means is that I have a 0 for all of the columns that are not true, and then a 1 in the column that is true. So the first passenger was a mister. We have a 1 here. Second passenger was a missus. We have a 1 in that column and 0 in all the other ones. I'm going to ask you kind of a tricky question that is even very hard for my Berkeley students to answer many times. So I said that we needed to take the title column and convert that to numbers. Why didn't I encode my title column and say that Mr. is going to be 1, Mrs. is going to be 2, Miss is 3, Master is 4, and Rare is 5? Why did I create 5 new columns instead and only have a 1 here and 0 for the rest? Yes. So the answer now, and I'm reiterating for the people online, only so that they heard, is that if you're using neural networks, they cannot handle numbers that have a magnitude that is greater than the range between 0 and 1. This is true, not for this case. It was not the correct or the answer I was looking for. But neural networks, for example, when you have data that are on different ranges, so let's say that you had the salary of a person, the age of a person, you might also know how many siblings they had, something like that, the temperature outside. All of those will be on different ranges. What you do then, if you're going to use a neural network, is that you standardize the data. So you cast those ranges onto 0 and 1. And that is called standardization of the data. This is the advanced course, what we're talking about now. But that is not the reason why I'm doing this 0 to 1. It would still work with 1 to 5. That is not completely different from the other ones. Anyone else has an idea? And this is a tricky question, but I hope that someone can at least.
Can you repeat again?
So why don't I have one column here
Yeah.
that says title? And then I would map Mr.
As the
to be
one.
1, Mrs. to be 2, Miss to be 3, Master to be 4, and Rare to be 5. Why did I create 5 new columns? It's a little bit counterintuitive, right? Because we could do the mapping with like, okay, Mr. is going to be 1, Mrs. 2. The reason for that is because we don't have any type of ordinal relationship between these. Again, terminology. What that means is that we cannot say that Miss is double the worth of Mr. We don't have that kind of relationship between the titles. So if we say that Mr. is 1, and then that Master is 4, what we're telling the machine learning algorithms is that Master is going to be worth 4 times as much as Mr. And that doesn't make sense. So because of that, we need to create 5 new columns instead, and all of them become binary columns. It can be 0 or 1. So now you know why I did that, and that's a step we need to take. The next thing that we're going to do now when we have started working on the text columns is that I'm going to map the gender, male or female, only to a 0 or 1. Here we only have a binary column. Perfectly okay to only be 0 or 1. We don't need to create 2 columns. Then it looks like this. Another problem that I highlighted earlier was that we had the age column. And we had many missing values in the age column. We had almost 200 people that we didn't know the age of, and we will need to populate those missing values so that they can work with the machine learning algorithms. We can see here that for all of the columns, we have 177 missing values for age and 2 missing values for embarked. What I'm going to do here is that I'm going to fill these missing values. So I'm taking the age column, fill the missing values, and I'm going to fill them with the median of the age column. So that was the 50th percentile. So all the missing values are now going to be the median. That's kind of a crude approach. We could do it a lot more sophisticated. So we could look at subgroups of passengers. For example, all females from the working class, what is their median age? And then we can find all of the females from the working class where we have missing values and populate that. I'm mainly doing this for speed. But if I competed at Kaggle, I would have a more sophisticated approach for it. But now we have filled out the missing values, and we can actually use all of our samples where we didn't have values for the age column. And if we run this again, we can see we have 0 missing values now for age. I have talked a little bit about the fact that we want these algorithms to generalize. We want them to find patterns in the data. And if we have some data that is very unique, it will overfit to that data. Now, since we only have 891 samples in total, it's actually very good to build up categories that could help with the generalization. So I'm going to do that for the age column. Here, I'm going to split up the age column in 5 buckets. And these buckets will be 0 to 16, 16 to 32, 32 to 48, 48 to 64, and 64 to 80. The reason for this is because I want my algorithms to be able to pick up patterns according to where you were in life approximately. And not only to have a specific, like, okay, I was 32 years old, and then you have someone who's 34, and it might be a difference between those two. and it would add some noise because we don't have a lot of data. So when you're 0 to 16, I would say that you're a child, a kid still. 16 to 32, that's a young adult. 32 to 48, adult. 48 to 64, middle-aged, and then you're older if you're 64 to 80. Here I've also plotted a survival rate to actually show you that it contains a lot of information, what age group you're in. So if you were a child, you had a 55% chance of surviving. Young adult, only 34%. Adult, 40%. 43% if you were between 48 to 64. And then 64 to 80, it's less than 10%. So we heard an hypothesis around that. Someone had seen the movie, people were freezing, they didn't make it. This is what the data tells us. And that's why it's also important to split up into these buckets, because then we can see the patterns emerge. We can also do very fancy analysis. So this is more for a statistics course, but I can show it to you only like in 10 seconds. What I have here are two distribution plots. And what they show you is either if you survived, then you will have the orange distribution here, or if you died, you will have the blue one. When the blue one is above the orange one, it means that you were more likely to survive. Die, I mean. If the blue one is above the orange one, you're more likely to die, and vice versa. So here we have that for males when gender is equal to 0. So if you were a kid and a male, you were actually very likely to survive. And then when you were a young adult, up to like 35 or something, you were very, very likely to die. And then it's almost the same across. The pattern fluctuates for like girls or children that are like girls. They were more likely to die. I think that could be noise in the data. To me, that doesn't make sense, at least. That's the first thing that we have discovered so far that I don't have a good like explanation for. That can happen at times. Then it's almost the same across when it comes to young adults. Then when they get a little bit older, they are much more likely to survive than their male-like counterparts. So these are very fancy, nice plots that you can make with Python as well. That takes a little bit of programming to do. Feel free to explore that if you want to. Now we're going to map all of these age groups to different numbers. When we had the title, I created new columns. But here we actually have an ordinal variable. So we can compare the first age groups of children with the young adults, and then the adults, middle-aged, and the old people. So I'm going to map people who are between 0 to 16 to be in group 0. Young adults to be in group 1, adults group 2, etc. So we only create one column here. And then the result looks like this. We're getting close now. This is kind of beautiful. I'm very happy with the appearance of our data frame right now. Another thing that I want to concentrate on in order to make sure, again, that we can generalize to patterns we have in the data is to look at the travel party size. So the columns we're going to be inspecting are parents and children and siblings and spouses now. So I'm creating a new column here that is called family size. And that's going to be the number of siblings and spouses, parents and children that you had on board, plus 1, because you yourself is part of your family, hopefully. Then we can look at the survival rate depending on family size on board of the Titanic. Now, what we can see here is that if you traveled alone, if your family size was 1, you only had a 30% chance of surviving. If you had 1 family member with you, it was 55%. 2 family members, 58%. If you had 3 family members, it was 72.4%. That's amazing. 5, it's only 20%, 13%, and then 0% for very big families. My hypothesis here is that if you had a very big family size, then you were actually from the working class or you were low under deck, and your likelihood of surviving, getting all of your family together, finding a lifeboat, etc., was not that good. However, for small sized families, you could collaborate, you could help one another. And that seemed to be beneficial, at least if you compare it to people who traveled alone. Again, we can look at the actual absolute numbers, and you can see here, people who traveled alone, very likely to die. If you had kind of like normal sized families, your chances were really good. And then if you had bigger families, almost all of them actually perished when the Titanic sank. Again, we have maybe too many categories here. We have some categories where we only have 2 or 3 samples of large family sizes. So I'm instead going to convert this to a binary number. And that binary number is going to be called is alone. That's a new column in our data set. If that is 0, that means that you had family members with you. Then that is not true. If family size is equal to 1, or if is alone is equal to 1, that means that you traveled by yourself. So what we're going to use for our machine learning algorithms is this. Did you travel by yourself? If that is a no, you had family members. Your chances of surviving were 50%. However, if you were by yourself, it was only 30%. Again, in order for it to generalize. What we can do then is to drop the columns, parents, children, siblings, spouses, and family size. And we end up with this. Now we are very, very close to being done with the pre-processing of the data. But if you remember from yesterday, I told you that for every machine learning project that you do, the part that takes the most time is processing the data, cleaning the data, getting it into shape so that you actually can use these statistical models, neural networks, machine learning. And we're still on that journey, only cleaning data, organizing it, coming up with hypotheses on what is important. And this is a little bit of a side note, but what you also can do is that you can construct new features out of existing ones. So if you come up with an hypothesis that, for example, how old you were and what class you're from, if you multiply those two together, so if you're very young from the upper class, because the upper class is indicated by a 1, and then now we have age groups that went from 0 all the way up to 4. We had 5 different ones. If you multiply them with one another, we will have an indication how likely you're to survive or not. Because children or young people from the upper class might be more likely to survive. And if you're very old and from the working class, you might be less likely to survive. So that could be one hypothesis. And in order to get the algorithms to look at that pattern, we will need to create this new column here. And then we can see I'm only multiplying these two numbers here and creating a new column that is called age times class. And we can see if we have some variability in the survival rate for this new one. And as you can see, some of these categories tend to be much more likely to survive, and some of them are much more likely to die. So maybe we did something useful. We have one column left, and that is the port of embarkation. So we haven't done anything yet with the fact that some people boarded in the UK and some people boarded in France. Here you can actually see the trip of the Titanic. So 10th of April in Southampton, it started its journey. It went to Cherwell the same day, and then it took 1 day to reach Queenstown. And then after 4 days, it collided with the iceberg outside of New York. So now if you remember again, when it comes to the embarked column, we actually had 2 missing values for that one. I don't want to throw away those 2 samples, those 2 people. So what I'm going to do for them is that I will take the most common port or the mode in the port column, and I'm going to populate the missing values with the most common port. And we can also look at what port that is. I stored that in frequently used port. That was Southampton. That was the most common port. Then if we look at the survival rate for the different ports, it looks like this. So these are the actual numbers. We can see that if you boarded in Southampton, you were very likely to not make it. If you boarded in Cherwell, it was almost a 50-50. At least that is what it looks like. And then Queenstown, more likely to die, but not as severe as for Southampton. So there was something about the French people. Yes. Same.
Could it be that more people boarded from one place?
That shouldn't matter, right? Because if even if only 10 people boarded from one port, it should maybe be reflected the same as the general for the whole ship if it wasn't a difference.
Maybe the sea just doesn't like people from Southampton.
Wonderful hypothesis. I haven't heard that before.
So the Kraken eat all the people from Southampton.
Yes.
I'll put that on. There's a museum there as well, so I wonder if they know.
They probably looked at the data. No, but if we look at the probabilities here, we can actually see some discrepancy that tells a story at least. So if you were from France, you had a 55% chance of surviving. If you were from Queenstown, it was 39%, and Southampton, 34%. So there is a huge difference. And I don't know if that is because the French people were obnoxious, or maybe they tended to be more from the upper class, or cabins that were at the top of the ship, etc. They spoke French, nobody understood, and they were like,
Or maybe there were more males from Southampton who boarded.
exactly.
Yeah.
No, but we could also do that correlation analysis. Sorry, Stephen.
The people from Southampton probably more help.
Yes, they were more gentlemen from Southampton. You should be proud of that. So now we know that fact, that this column actually carried some information. We also need to do something with the embarked column. So my question to you now is, how are we going to encode this into numbers? Are we going to assign S to be 1, C to be 2, and Q to be 3? No. Thank you. That's a clear no. Just as for the title column, we cannot say that Southampton is worth 2 times more than Queenstown. Doesn't make sense. So instead, we're going to create 3 new columns and do binary and or 1 hot encoding again.
So this means that Leonardo DiCaprio.
We will have to check Wikipedia. But so this is what it looks like. Here, I have also dropped the embarked column now. We don't need that information anymore. All of that is stored here. We know that this person boarded in Southampton. We have a 1 here, a 0 for the other ones. And now, when we can see this, we are very, very happy. Because here we only have numbers. All of them are in categories. They are on similar ranges. None is like up to 200, so they won't throw off any type of algorithm. And now we can do our machine learning. So this is the process we have to go through, at least with this data set, to make it understandable for our algorithms so that we can train them so that they can find patterns in the data to make predictions if a passenger survived or died. Now, one last thing that is important to look at before you actually feed this to models is to see the correlation between features. So remember, features, they were the columns. Correlation means how much does one column vary in accordance with another one. So let's say that one value, that could be age, if that goes up, does another value in our data here go up at the same time? Then we have a positive correlation. Correlation values go from -1 for perfect negative correlation up to 1 for perfect positive correlation. And if we have a 0, it means that they are uncorrelated. We cannot find that they vary together with one another. And if you find that some features correlate too much without you being able to explain it, then you will need to throw away one of those features. Otherwise, they can basically ruin your prediction models. So what I want to do now is to look for high correlations here and see what we can find. The largest one is probably this one here, minus 0.87, very close to perfect negative correlation. And that is the Mr. column with the gender column. That makes sense, right? It should be a negative correlation because when Mr. is 1, then the gender column is going to be 0. Why isn't it minus 1? Also a tricky question. No. We have another male column, and that is master. So if we didn't have master, it would be minus 1.
Some Mr. survived.
Yes, some Mr. survived, but still we're only looking at the correlation between gender and the Mr. column now. So we're not looking at the mapping against survival.
And also in the where, we also have a
Exactly. So nothing here, at least to me, stands out. I mean, we have the age column that's well correlated with age times class. That makes sense. We're multiplying the values. So nothing seems to be off, at least according to me. Feel free to correct me when we're done with this. But with that, we have come to the point where we're now going to do actual AI. And when I showed you the full ecosystem of how you build AI systems yesterday, I said that the algorithm was a very small component of the large system. This is that small component that we're going to design now. This is the model that will make the predictions. And we're not only going to create one AI model, we're actually going to create 7, as I said in the beginning. One is a logistic regression model. That's almost like linear regression, but for classification. A very simple model. We have k nearest neighbors. What that model does is that you choose the number of neighbors. So it can be 2 neighbors, 3 neighbors, 4 neighbors, etc. That's the k that stands for an arbitrary number. And then you will look at the whole data set in a hyperdimensional space. You will measure the distance to other points. And you will say, okay, this point that you're looking at is close to these. Let's say that we are using 4 nearest neighbors to these 4 other samples. Were they likely to die? Or were they likely to survive? And that's how you make the prediction. Support vector machines is an algorithm from UC Berkeley. Very fancy. In a hyperdimensional space, you look at the data and distances to decision thresholds, etc. This, to go through all of these algorithms would take me a semester. We don't have several months together, unfortunately. But I'm going to do my best at 30-second pitches. The Perceptron Model is a neuron, and that's one neuron in a neural network. When we talked about the biggest neural network models yesterday, like GPT-3, I said that they had 150 billion parameters. Here we only have 1 neuron and not 150. So a very simple model. Gradient boosting, or XGBoost, that's a tree-based model that becomes a decision tree when you make decisions according to how old was the person, what socioeconomic class, family size, etc. And then you build these trees and you make a decision from the trees that you train. And you try to train the trees that are making decisions to fit the data perfectly. Random forest works the same, but you don't do boosting. And when you're boosting trees, you're looking at residuals and errors. Last but not least, we have neural networks. And we saw that yesterday. We had the layers with the neurons. The information gets fed from one hidden layer to another one. And at the very end, we did the classification. So then we looked at classifying cats and dogs, right? And at the end, we got a probability of either a cat or a dog. Here at the end, we will get a probability of survived or died. And that's going to be the case for all of these algorithms. So are you ready to do some real AI? This might be the first time any of you have seen it. Now, we're going to train mathematical functions, right? And everyone knows a function. We talked about the straight line yesterday. You might have some y values that is equal to a slope parameter, let's call it k, times x, that can be the input to the function, and then plus some intercept that can be called m. We need to have some input to the function. That's going to be all of the columns except for survived. That is the actual values that we're going to use in order to make our prediction. We're not going to look at survived to make the predictions. So our inputs to our functions are going to be all columns except for survived. I'm doing that here. And then the output, what we want to predict is if they survived or died. So that's going to be our y. So in total, we have 891 passengers. We have 13 columns in the input. That's embarked, all of the titles, gender, age, etc. And then in the output, we only have one column. And that's either a 0 or a 1 for if they survived or died. Now, what we need to make sure when we're training algorithms is that we're not overfitting to the data set that we have at hand. So if I was to use all of these 891 samples, and I trained an algorithm to make predictions if they survived or died, I can take the most complex neural network in the world. I can take one of those with billions of parameters. And I promise you that I can get a perfect score on this training set with 891 if I predicted the same samples that I had trained on. It's very easy to pick up all of the nuances if you have billions of parameters, because then every parameter in the network can represent one value from every passenger. Exactly. And if we're memorizing the entire thing, then we are overfitting. That's not what we want to do. We want to take our algorithm, submit it to Kaggle, and they will score data that we've never seen before and see how we perform. So in order to simulate that process, we need to keep some data to the side. So what I'm going to do is that I'm going to split up my training set now. I'm going to keep 20% of the data to the side. I'm not going to train on that. And then I'm going to evaluate my accuracy after I've trained my model with 80% of the data on the 20% of the data that it hasn't seen before. That's a real world situation. If we train that computer vision model to be able to classify cats or dogs in images, we're not interested to take the images we already have labels on and we know that it's a cat or a dog and classify them. But we want to take new images that the model hasn't seen and we want it to perform well. So that's how we're going to evaluate the accuracy here now, on the 20% of the data that we're not touching when we're training the machine learning algorithms. Make sense? Perfect. So then we're going to train on 712 passengers, and we're going to evaluate on 179. And on these 179, then we're going to get an actual accuracy. So we're going to see how we perform. And what was the baseline? Does anyone remember? What did we need to beat? 61.6. So we need to be above 61.6. Otherwise, we're not seeing any patterns in the data. Then it's better to have a model that always guesses die. Now, you will probably be kind of amazed how easy it is to train machine learning models and AI models, because you only have this step-by-step process. First, you create the empty model object. It will have model weights and parameters that can be adjusted to make decisions. But it will only be an empty model. It will have like random weights in the beginning. Then you train the model. That means that you show the data where you have the actual, like, did the person survive or not? And you show them all, these are the socioeconomic classes, the age, the title, etc. You do that for many iterations. That's the training phase. Then you take data that you've kept on this to the side and you predict on that. So you predict on unseen data, and then you evaluate the accuracy. So how did we score on that data we didn't train on? 4-step process. And this is how simple it is in code. So first of all, we create an empty model object. Here I'm going to use logistic regression. You remember at the very top, I imported a lot of machine learning models. One of them was logistic regression. Then on the second line here, I take logreg, that is my logistic regression model. I run the method .fit. That means that we're going to train it. I'm feeding in the training data. So bear in mind when it says X train here and Y train, those are the 790 samples that we're going to train on. And then predict and evaluate. I can do that on one line of code, and that is logreg.score. Then we will first predict. I will only feed in X validation. That's the data we kept to the side, the 179 samples. And I will compare my predictions with the true values that we also know. Because the data we have on the side, we have the actual outputs if they survived or died. And that's how we can get an accuracy. So how many of the predictions that we made were correct? What accuracy do you think we're going to get? I want one person to guess. What did you say? The 50% would be really bad.
95%.
95?
It has to be over 61.
Yes.
90, 97.6.
80, 97.6, 95. One more guess. 90. Okay, moment of truth. How good can we? 78.2. Amazing. So logistic regression is kind of simple, I said. Then we have k nearest neighbors. I explained that algorithm kind of intuitively. All of you understand it now. We only take the closest samples to the one we're trying to predict. The number of neighbors I'm going to evaluate are 5. Same process here. We create an empty model object. We train it on training data, and we evaluate it on the data we kept to the side. The accuracy we get for k nearest neighbors, 81.56%. Still in your ballpark. Congratulations. Support vector machines. Same process. Create the model, train the model, evaluate. 80.45%. Perceptron model, I said that there was a one neuron in a neural network. We create it, we train it, we evaluate it, and we get an accuracy of 74.3%. So now it's dropping, but it should drop because that model is too simplistic. Then we have gradient boosting. So this is actually an algorithm that many times is being used in order to win Kaggle competitions. Here I'm saying how many estimators I want to use. That's the number of trees to make decisions. And I'm going to take all of those decisions for the 1,000 trees in order to do a classification. But same thing again, create the empty model object, train it, evaluate it. 82.12%. I think that was the best one so far. Then we have random forest that is very similar to gradient boosting. Number of estimators, I lower it to 500 here because it's prone to overfitting. But I instantiate, I train, I evaluate. 81.01%. So those were the simple models. This is traditional machine learning. This is how people did statistics and analysis prediction models in the 90s. Now let's turn to neural networks. So in order to create a neural network, this is a little bit more complicated in code, but it's the same procedure. Here I import my models. I'm using TensorFlow from Google in order to do so. Also a tool that is free to use. Importing the sequential model and then a dense layer. So in a neural network, when you have a dense layer, that is a layer that is connected to its input. For example, all of the pixels when it's a cat or a dog in an image. We import that. That takes some time. You can see the star here. It's evaluating. Then I'm creating an empty model object. So I say my model is going to be sequential. To that model, I'm adding the first hidden layer in my neural network that has 300 neurons. For the perceptron, we only had 1. And the input shape, we're going to look at 13 columns. I also have what is called an activation function here. That is to introduce nonlinearity in the network. Don't care about that. But if we didn't do that, it would be a linear regression model. I'm adding my second hidden layer with 100 neurons, third hidden layer, 50 neurons. And then at the end, I have one neuron, and that's a sigmoid function, not a ReLU one, that will turn into a probability. So if that is close to 1, we're going to predict survived. If it's close to 0, we're going to predict died. So there I've created a neural network. Then we need to train it. In order to train a neural network, we need to say how it's going to be trained. I'm going to do binary cross entropy here. Binary because we have two outputs, either 0 or 1 for died or survived. Cross entropy because it's a classification task. I have an optimizer, so I will need to tell it, okay, how are you going to train your weights? That is called Adam. And I want to measure the accuracy. That's what I want to improve here. Then model.fit on the training data, just like before. And I'm going to do this for 50 epochs. I'm going to show the full data set 50 times. Very beautiful, very quick. We're already done. We can see some status updates here for every time that we show the data set. And then we evaluate this model, and that's with the code here. This is only comparing, okay, when we make predictions on the data it hasn't seen, is that similar to the data that we know is true? 80.45%. So one thing that you should take with you here now is a very famous theorem in machine learning and AI. And that is that there is no free lunch in machine learning. What that means is that there is not one hammer that is the best tool for all the different problems. We cannot say that neural networks are going to be the superior algorithm for some problems. Here we could see that the random forest and the gradient boosting algorithms, they were better than the neural networks. And that is many times the case, that you should use simpler algorithms to solve many problems. So don't believe the hype when someone comes and says, oh yeah, there is this new algorithm and it's beating all the other ones. Actually do try your full toolbox and everything that you know. And that's important for those of you who go into university and maybe do this kind of thing. Don't believe that only the new tools are the most valuable ones. The random forest model, because that is a decision tree that splits up according to all of the different columns we have with socioeconomic class, age, gender, etc. We can actually look at what columns are the most important ones in order to predict survived or died. That means that we can get an indication on what column carries the most information in order to do our predictions. So which column do you think is the most important one in order to say if a person survived or died during the accident? We have gender, we have title. So we have heard class 2 times. Gender. Gender. So 2 for gender, 2 for class. Anyone else? I want one more, because otherwise it's a tie. Gender, okay. So with this code block, I'm only going to plot the most important ones. And it's actually the one that I created, age multiplied by class. However, that can be a little bit misleading, because in that column, we have information from 2 other columns, right? Second most important is actually the title misses. Then we have miss, and then we have age, is alone. So we don't have gender here, unfortunately. But gender is also baked into the titles, right? So that might be more informative than that binary column. And now we are at the very end of the notebook. And I have one last question. And that is, why do you think that the machine learning models that we have are maxing out with their prediction accuracy around 80%? The best models that I've seen in the world are like 89%, up to 90%. If you don't cheat on this competition, it's possible to also trick the competition. I'm not going to tell you how to do that. But if you're actually making predictions, let's say that the best in the world is 89%. Why do you think we cannot do better? Yes. So what data would you collect in order to make better predictions here? How about the cabin data and the fare data, like ticket price, etc., that has been used in the best solutions. So it still caps out at like 89%.
What about human behavior? Because you have to decide who gets some votes.
And how would you get human behavior into Excel? Yeah, maybe we could do interviews. Unfortunately, most of the
That's why it can't.
exactly.
What about number of lifeboats available?
Yeah, number of lifeboats would be good, and that's more for like the average survival rate, maybe, and where they were located, maybe how close you were from your cabin to that one, if you could calculate that correctly.
Things like mobility.
Yeah.
How you can find it to get from point A to B.
Yeah, maybe how strong you are, your record sprinting 100 meters, or if you had a broken leg or not. Anything else that we could collect?
Whether iceberg hit the boat.
Weather?
No, where it hit the boat.
Yeah, where it hit the boat, exactly. And where you were at the time when it hit. But still, if we had all of this data that we have discussed now, and maybe we even knew like the empathy of people, how likely they were to help one another, if they had any trouble moving around, if they were very close to the lifeboats, we would never get perfect information into an Excel spreadsheet to be able to say what is actually happening in the real world. And this is something that I find very fascinating, because behind all of the events that played out here, we actually have human stories. So we have limited information on the humans, and we try to generalize to make predictions. But we cannot know exactly how a person in a panic situation like that, how they acted, what they did. So I have two examples here. The first gentleman I want to introduce you to is John Jacob Astor. He was the person that paid $512 for his ticket. And that is around 35,000 US dollars in today's value. He also, in cash on him, had around $100,000. Now, because he was from the upper class, because of where he stayed on the boat, and all of the characteristics related to John Jacob Astor, that makes all of our machine learning algorithms that we have trained now, they are predicting that he survived. And they should do that, because he has all of the characteristics of a person who would actually survive the accident. However, that was not the case. And yeah, when his body was recovered, they got the cash, a lot of diamonds, etc., that he had on him. But he saved a lot of people when that happened and stayed on the boat. We also have Olaus here. So he was a Norwegian sailor. He was from the working class. He was in the age group that was very unlikely to survive. And all of our machine learning algorithms, again, they predict that he was going to die. However, he jumped from the ship into the freezing cold Atlantic water. He swam for 20 minutes, and then he reached a lifeboat. We cannot take that into account with our machine learning algorithms when we only know the age, we know what they paid in order to board the ship, where they embarked from, etc. But Olaus here, he survived. He could tell the story. A lot later, what happened on the ship, he died at age 94. He was in North Dakota. He had 4 kids afterwards, etc. So this is almost like a happy ending. For those of you who have seen the Titanic movie, yeah, spoiler alert, Leonardo DiCaprio doesn't make it. it's very sad. But here we have a happy ending with Olaus. And those are all stories from like human events that play out, and our AI models, the artificial intelligence we have, cannot completely map out the real world. Not yet, at least. And I don't think it's ever going to be able to do that. So with that, I can take any questions. But yeah, wonderful to have shown you this. And now you have all seen how you actually create what is called machine learning, data science, deep learning, neural networks, and artificial intelligence, at least once in your life.